Hey, what's up, guys? Okay, so welcome to my analytic number theory video. Okay, so today I want to talk about the Mellin transformation, and basically I want to talk about inversion formula. Okay, so if you haven't seen my video, my video is about my YouTube video about some higher mathematics. And sometimes I do some coding, sometimes I do some physics. I do whatever I want. Okay, so previously I defined this is so-called Dirichlet series. So f of s, f of n divided by n to the s. If somebody give you the any arithmetic function, so f of n divided by n from n to the s from 1 to infinity, the famous example is a Riemann zeta function. And previously I also said this m of f of x. This is a summatory function. Usually f of n, you sum from n less or equal to x. So if you want to estimate the growth of the arithmetic function, then you will intermediate related to the pole of the Dirichlet series. Okay, and their relation is basically from this equation that I proved previously. Okay, so simply speaking, is that the growth of m of f of x is related to the poles, or basically the analytic structure of the Dirichlet series. Okay, so this is why, for example, the zeta function is interesting, right? Because the zeta function, the pole of the zero of the zeta function, the zero of the zeta function, or the pole of zeta function, will basically give you the growth of price. Okay, so this is the future topic. Okay, so today the inversion formula means that I want to find the inversion, right? So now if somebody give you m of s f of x, then you can compute this. What is the relationship of the inverse function? Okay, so the idea is called Perron's formula. Yeah, previously I think I have a video that talk about Perron's formula using a complex analysis, so I will post a link below. But today, in an analytic number theory, we need a more fine version. Okay. Okay, so yeah. Okay, so the more fine version, basically, let me just write down. So let me just also define this m1 f of x is also common, which is you sum from this. Okay. Okay. So theorem. So first theorem is that you can define IYT. Okay, so let's say c is greater than 0 and the t is greater than 0 and the y is greater than 0. So this is 1 over 2 pi I. So this is a complex analysis residue, c plus it, c minus it, y s ds. Okay, so this is the first IYT. And I also define I of y to be 1 over 2 pi I, c minus I infinity, c plus I infinity, ys s plus 1 dy. Sorry, ds. Okay, so this is a two function. And the first theorem says that if you do IYT minus 1, well, that's equal to yc pi t log y if y greater than 1. And if the IYT, well, that's equal to y to c pi t log y, take absolute value for 0 this. Okay, so what it means is that if you take t to be infinity, then this y to s divided by s ds will be if y greater than 1, will be 1. Okay, otherwise it becomes 0. Okay, so simply speaking, so if you want to prove this using complex analysis, that you basically just get the following, right? You get this is you get let's say 2 pi I c plus I infinity, c minus I infinity, y to the s dy, which your results will be if y greater than 1, you get 1. If y greater than less than 1, you get 0. Okay. Okay, you can prove that when the y equals 1, I think it's half. Check by yourself. Okay. Yeah. So, but this is I think this one that if you want to prove this one, that you can use your sorry, not high school, undergraduate complex analysis. Let me just quickly say whether it's easy or not, right? So let's say if y greater than 1, if y greater than 1, right, I can pick the left-hand side contour. Okay, so this is my integration. Okay, so now I will capture a pole when s equal to 0, right? So you get 1, right? So this is true. And for y less than 1 and greater than 0, that you will pick the right contour, so you will not close any poles, right? So this gives you 0. So this is the standard version that called the Mellin transformation, and this can be easily proved by this is trivial. Okay, so trivial by picking the correct contour. Okay, but for this one, which this is the quantitative version. So this one is important if you want to learn more about analytic number theory, because you are not just saying something. Oh, this guy will be 1, right? Because you need to you want to find the error. Okay. Okay. So which I'm gonna to prove this, and also okay. So let me just write down another theorem, which is you can compute this I1y. So if y greater than 1 is 1 minus 1 over y, otherwise 0. Okay, so let's prove the first one. Okay, let me just use red. Okay. Yeah, I should try to prove this. I should try to prove this, right? But okay, so let me just write down. Oh, okay, so let me just try to quickly sketch the proof, because I mean the proof is not difficult, right? Just a little bit tedious. Okay, so let's just assume that y greater than, then let's assume that y greater than 1. Okay. All right. So and I want to find this. Right. So I know that if I take the left hand side contour, that I will get something, right? So, but let's choose this contour to be, let's say this is c plus it, c minus it, c plus it. So contour, and let's do this, right? Let's take this b plus it and b minus it. Okay, so we pick this to be contour, which is a rectangle, and what? Okay, so you get four of these. Okay, and we are going to take, let's say, b to infinity. Okay, so the simple observation is that you can try to argue this. You can try to argue. Let me just see how do I do this. Okay, so let's consider this one, right? So this section. And then let's say your function is this, right? So your y to s divided by s. It should be simple, right? It's bounded by, let's say, y to a b to a b. Okay. So if you take b to be 0, then this guy, if you take b to be 0, this is b. So if you take, let's say you take. Oh, sorry, I'm stupid. What's going on? What's going on? Okay. Right. So if you take b to be 0, then sorry, b to be let's say b go to negative infinity. Sorry. So if you take b to negative infinity, then this guy will be 0. Okay, so you don't need to care about this. Okay. So all the arrow term comes from these two, right? All the arrow term comes from the left, the upper and the bottom. Okay. So this guy is bounded by 1 over 2 pi. Let's say y t d sigma, right? So let's check. So y to s y divided y to s divided by s, and let's say in this or in this region, right, it's bounded by the real part, right? So the real part will be what? Will be y to the c, right? So this guy, let's say this guy is bounded by y to the, let's say sigma divided by t. Sigma is a real part. Okay, so this guy is sigma divided by t d sigma. Okay, so this just means that s is sigma, right? Because okay, so because in this that just a line, right? So it's just the same as real integral. And right, and the bound the s of this is sigma plus it, right? So I bound this by t. Okay, so this is less or equal to say this is b to c, right? So this is 1/2 pi, and y c to the negative infinity y sigma t d sigma. Okay, so this is y to the c 2 pi t log y. Okay. Okay, so simple proof. Okay, so that's it. And there's a factor of 2, right? Because in this one that I only consider these things, and you can consider 2, right, twice. Okay, so hopefully this is clear, right? Because your y of s divided by s, I can, if I take the absolute value, then this s will be real part, and then the s will be the modulo. So in this case, I can only preserve, I can use the complex part. Sorry, the imaginary part. Okay, so now it is proof this. Okay, so this is for y greater than 1, and then for y less than 1, that you can just simply use the same thing, right? So that we already proved this. Okay, so for this I1 of y, let me just quickly prove it. Probably it's not difficult. I mean, you can try to prove this. Okay, so maybe, okay, so let me just quickly prove this. I think it's not difficult, so let me just sketch it. Ys ss plus 1 dy, right? So we do the same thing, right? So if let's say y greater than 1, then you do this, right? So now you capture 2, right? You capture as 0 and s equals to -1, right? So this I1 of y will be the residue of y to the s ss plus 1. Let's say residue s equals 0 plus residue of ss plus 1, s is -1. Okay. And first of all, this one that you take 1, right? And for this one, you take 1 this. Okay. That's it. You need to check this arc is 0, right? But it's trivial because y is greater than 0. So if you take it to be infinity, then arc will be 0. Okay, and if let's say if y is let's say equal to 1 greater than 0, then you take the right part, right? So now you take you get 0. Okay, get 0. Woo! Okay, so yeah, so we are very happy that at least we proved. Yeah, we're happy that at least we proved these two functions. Okay, so now let's go to the Perron formula. Okay, so our main part is this Perron formula. Okay, so Perron formula has 2 versions. One is for this mf of x, one is for this m1. Okay, so let me just stay about this m1. Okay, so theorem tell you that basically m1 of x will be 1/2 pi I c plus infinity, c minus infinity, f of s, right? So we do something like this. Okay, and assure that you need to assume that f of s is converge, right? So after some critical line, that f, so not critical line, after some straight line, the f of s absolute converge. And then this you can write this and write this. Okay, and prove this. Okay, definitely your C need to greater than, let's say, absolute convergence. Let's say this is after this sigma A, this Dirichlet series converge. So your C need to take it in greater than sigma A. Okay, technically you can take C to be max 0 sigma A. Okay, but let me assume that sigma A is greater or equal to 0. Okay, and this is true for any real number x greater or equal to 1. Okay. Don't worry, the proof is not difficult. Okay, the proof. How should we do this? Okay, so let's consider this. So you just directly plug everything you know, right? Let's say you run f of s to be summation f of n to the s, and from 1 to infinity, just plug it. I mean, if you haven't studied the advanced calculus, it seems like everything is just calculus. But if you learn about like the major theory or something that in some time that it will make you very crazy. It will make you crazy. Right? For example, if I want to exchange this integral with a summation, then I need some kind of uniform convergence or whatever m test. Right? But usually in the I usually in a lot of proof that the people don't do this kind of things because otherwise that the mathematics will be so difficult. Okay, so we write this list. Yeah, so this part maybe use m test or uniform convergence. Okay. So this part that you do the residue, right? You use the theorem. So this is I1, right? So which tell you that this is just n from 1 to infinity, f of n x I1 x divided by n. Okay, and this part is non-trivial, right? This part is only this 1 over 1 minus x divided by n if x divided by n is greater than 1. Okay. So which tell you that this is just f of n x minus n, right? Because this is x times 1 minus x divided by n, right? Previously that we just proved. So you will use this, so we get n less or equal to x. Okay. When n is equal to x, because our condition. Remember our condition. Okay, so let me just write. Our condition is this, right? So in this case, that you're gonna to use this part, right? You're gonna to use this x divided by n must be greater equal to 1. So greater than 1. Okay, which is as less this. Okay, and then you are not worried about 1, right? Because 1 in this part is already 0. Okay, so this is just m1 f of x. Nice. Okay, and by the way, you need to prove this is uniform convergence, so it's not trivial, right? You need to take the absolute convergence to make sure that all this proof is technically correct. Right? But if you just forget about it, like some technically something that you can try to do this. So you can try to prove these guys absolute convergence if you take the absolute value. So now you can exchange with the integral. But I'm not going to do this. You can try to do. It's not difficult. Don't worry. Okay. Okay, so let's talk about the second Perrons formula. So basically, it's second Perrons formula. Perrons formula for mfx. Okay, so theorem tell you that mfx is 1 over 2 pi I c minus infinity c plus infinity f of x s divided by s ds. Okay, and then you also do the same thing, right? You need to assume that this f of s is absolute convergence. Otherwise, that is still make you crazy. Okay, so proof just directly follows. Let me just go to this page. So let's just quickly prove it. So obviously that you just use the first formula that you just plug in. So so somehow once you understand this proof, then everything becomes somewhat almost trivial because okay, you got something like this, and sorry, I forgot about this s. Is it? Yeah, okay. Yes. Okay, so let me just write down. So you get 1 over 2 pi I, and from 1 to infinity, f of n, c minus infinity, c plus infinity, x divided by n to the s ds s, right? So this is just our I of x divided by okay, and t, you can choose t to be infinity. Okay, so do the same thing, right? So these guys survive when x greater or equal to n. Okay, or greater or equal to. So these guys just summation f of n less or equal to x, which is m of f of x by our previous lemma. Okay, so now we have two kind of Perron formula, and we also prove it. And You can try to do the same thing for arrow term, but I skip. Okay. But let me just make a remark. Okay. So let me just quickly so about remark. This remark that we will use is that if you write m of x, right, using the finite t, which is I just say is, so this is why we need to derive the arrow term. If I write it as this, then I should get some arrow term that respect to t. Okay. And if you do the Perrons formula here, that you use t, that you get some arrow term, right? So easy to see that this arrow term is bounded by using our previous results. Xc divided by t, summation n from 1 to infinity, f of n, n to the c log, x divided by n. Okay, so this arrow term is the proof just using our previous results about the arrow term of I of x divided by n, and then use just sum from n from 1 to infinity, f of n, so you get something here. And this arrow term will show in the prime number theorem in the future that we talk about zeta function. Okay, and with a proof scheme. Yeah, so this is you can try to prove it. It's not difficult. Sorry, you need to take absolute value. It's not difficult. You can try to prove it. Okay, so see you guys next videos.